Good morning, my dear students. Today's lecture, I am talking about randomized block design. The topic is designed for the B.SC 6th semester major students and C.B.C.S 4th semester generic students under Dibrugarh University. After completion of this lecture, you will be able to know the basic characteristics of RBD and also know the basic layout of RBD, the model used in this design, the assumptions used in this model, and merits and demerits of this design, and finally the interpretation from the ANOVA table of this design. RBD, that is randomized block design, is most widely used in agricultural research. The design is based on the three principles of experimental design, that is randomization, replication, and local control. The design is used when experimental material is not homogeneous and fertility gradient is moving in one direction. So the whole experimental area is divided into some relatively homogeneous groups, and these homogeneous groups are known as blocks. The treatments are allocated at random to the units within each block. That is, randomization is subject to one restriction, that is within blocks. Hence the name randomized block. The total variation is divided into three components, and they are block, treatments, and error. This is the layout of an RBD. So let us consider three treatments, and they are N, P, and K respectively. And both the three treatments are replicated 4 times. So a possible layout of RBD may be this. So we have 12 equal parts. See, both N, P, and K, all the treatments are replicated 4 times. So first we allocate the treatment P here. So we know that randomization is restricted to block. So the treatment P cannot allocate this block again. So first we have allocate the treatment P here. Next we can allocate the treatment P in this unit and this unit, and finally this unit. Similarly, we allocate the treatments N and P, N and K to the remaining units according to their replications. The fixed effect linear model used in this design is Yij is equal to mu plus alpha I plus beta j plus epsilon ij. Here the mu represents the general mean effect, alpha I represents the effect due to the IF treatment, and beta j represents the effect due to the JL block, and epsilon ij represents the error effect. Here we made the following assumptions. First assumption is that all the observations are independent, and second assumption is that summation of alpha I over I is equal to 0 and summation of beta j over j is equal to 0, and the error terms are distributed as normal variate with mean 0 and variance sigma square. Advantages of RBD. Blocking reduces the sum of squares due to experimental error, so it increases the efficiency of the design as compared to CRD. The statistical analysis is simple and less time consuming. The design is feasible with any number of treatments and blocks subject to the basic requirements of design, and it is a flexible design. Here are some disadvantages of RBD. The design cannot accommodate a large number of treatments. In many situations, the criteria for blocking or grouping is not easily selectable. So, in that situation, the design is not suitable. Usually, the blocks are not homogeneous as they are taken to be. So, one of the disadvantages of this design is that usually the blocks are not as homogeneous as they are taken to be. If the data on more than 2 plots is missing, the statistical analysis becomes complicated in this design. This is the ANOVA table of RBD-C. The first column represents the source of variation. Here we have treatment, block and error. And the second column represents the degrees of freedom. Here we have three treatments, so the degrees of freedom is obviously T-1. We have block degrees of freedom is R-1. And total degrees of freedom is RT-1 and error degrees of freedom is T-1 into R-1. The third column represents the sum of squared. Here ST square represents the sum of square due to treatment, SB square represents the sum of square due to block, SE square represents the sum of square due to error, and S square represents the sum of square due total sum of square. And mean sum of square due to treatment is obtained by dividing the total treatment sum of square divided by T-1, and block mean sum of square is obtained by dividing the block sum of square by R-1, and error mean sum of squares is obtained dividing errors sum of square by T-1 into R-1. Next we have to calculate the F statistics for the treatment and block. Here, this F statistics is calculated dividing the mean sum of square by error mean sum of square, and similarly the block F statistics for the block is obtained by dividing the mean sum of square due to block by error mean sum of square. Now this is the interpretation from the ANOVA table. See, if the calculated value of Ft is less than the table value of F for T-1, T-1 into R-1 degrees of freedom at certain level of significance, generally at 5% level, then we may accept our null hypothesis at that level of significance and may conclude that there is no significant difference between the treatment effects. Otherwise, we may reject the null hypothesis. Similarly, we may draw the conclusion on block effects. These are the references of this lecture, and thank you.